The percent ionization is a measure of the degree of ionization of a weak acid or a weak base. So if we start with the representative weak acid HA, if we take HA plus water, which exists in equilibrium with H3O plus and A minus, we would define the degree of ionization as the equilibrium concentration of H3O plus that results from the dissociation of the weak acid HA divided by the concentration of HA that was originally present in the solution. In other words, the initial concentration of HA. The percent ionization has exactly the same formula, except it's represented as a percent, so we multiply this ratio by 100%. Similarly, for a weak base, we take the representative weak base, A minus plus water, existing in equilibrium with its conjugate acid, HA, plus hydroxide. We would define the degree of dissociation as the equilibrium concentration of hydroxide divided by the initial concentration of weak base that was originally present in solution. The percent dissociation of the weak base, therefore, is defined as the hydroxide concentration at equilibrium divided by the initial concentration of the weak base, A minus, times 100%. In this example, we are asked to calculate the degree of ionization and the percent ionization for a 0.85 molar solution of ethylamine. The strategy for this is, number one, to write the balanced chemical reaction, two, to write the ice table for this reaction, and then to calculate the degree of ionization and the percent ionization. Starting with the balanced chemical reaction, we have ethyl ammonia, C2H5 and H2, plus water, existing in equilibrium with the conjugate acid, ethylammonium, C2H5 and H3 plus hydroxide. Next, we'll complete the ice table. So the initial concentration of ethyl ammonia is 0.85 molar, which was given in the question. Water is a pure solvent, so we just put a line through it. And the conjugate acid, ethylammonium, initially we don't have any to start with, so we write 0. Similarly, for hydroxide, we don't have any hydroxide to start with, so we also have 0. The change in concentration is given by X, since this is an equilibrium reaction. The change is X. For reactants, it's minus X. Water, again, pure solvent, so we just put a line through it. For the products, we have a change of plus X. And for hydroxide, also plus X. For the equilibrium concentrations, we just add up the columns. So here we have 0.85 minus X. Water, just put a line through it. For ethylammonium, we have 0 plus X, gives us an equilibrium concentration of X. And similarly, for hydroxide, we also have an equilibrium concentration for X. So this equilibrium line is the important part for solving our equilibrium problem. Next, we write the expression for the equilibrium constants, and it is Kb, since this is a base reaction, Kb equals the concentration of the products, ethylammonium, times the concentration of hydroxide, divided by the concentration of ethyl ammonia. You'll notice that water is not included in the equilibrium constant expression because it is a pure solvent. Next, we substitute the values in for the concentrations and the value for Kb, which is 4.3 times 10 to the minus 4 for Kb equals X times the initial concentration of hydroxide, which is also X, divided by the concentration of ammonia, ethyl ammonia, which is 0.85 minus X. So you can see that this will be a quadratic equation, and rewriting the expression as a quadratic equation, we have x squared plus 4.3 times 10 to the minus 4x minus 3.655 times 10 to the minus 4 equals 0. The next step is to solve the quadratic equation using the quadratic formula, which is x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. And plugging those numbers into your calculator gives you a value of x equals 0.0189. And as you may recall, x equals the hydroxide concentration from our ice table. So the hydroxide concentration is 0.089 moles per liter. Now we can calculate the degree of ionization, which is given by the formula, the equilibrium concentration of hydroxide divided by the initial concentration of the base, and that equals 0.0189 divided by 0.85, which gives us a value of 0.022, right? And rounding in two significant figures gives us a degree of ionization of 0.022. Similarly, for the percent ionization, it's given by the formula, the equilibrium concentration of hydroxide divided by the initial concentration of the base times 100%. Substituting the values in gives us 0.0189 divided by 0.85 times 100%, which gives us a percent ionization of 2.2%. Here we are asked to calculate the molarity of an aqueous solution of ammonia that is 4.2% ionized. The strategy we're going to use is to write the balanced chemical reaction, then construct an ice table, and finally to calculate the molarity. So the first step is to write the balanced chemical reaction. So starting with ammonia plus water exists in equilibrium with its conjugate acid, ammonium, NH4+, plus hydroxide. Then we can write an ice table where we have the initial concentration of ammonia. So this is actually what we are asked to calculate, the initial concentration of ammonia. So we don't know this value. We can use any variable. The most common is x, but in this case, I'll choose the variable b to remind us that it is the initial concentration of the base, ammonia. Next, we'll write the initial concentration of water, which is, just put a line through it because water is a pure solvent. Next, we'll have the initial concentration of ammonium, which is 0 because we don't start with any ammonium. Similarly, we have a concentration of 0 for the initial concentration of hydroxide. Now, the change in concentration is actually a little bit difficult to determine, except if we remember that the definition of percent ionization is the concentration of hydroxide at equilibrium divided by the initial concentration of the base times 100%. In this case, we're given the percent ionization as 4.2%. So we can simply rearrange this to calculate the equilibrium concentration of hydroxide. Rearranging gives us the equilibrium concentration of hydroxide equals 4.2% times the concentration of ammonia that we start with, which is B, as we said before, divided by 100%, which gives us a value of 0.042b, which we will place here as the equilibrium concentration of hydroxide. Knowing that, we can now calculate the change in the concentration of hydroxide, which would be plus 0.042b. And similarly for ammonia, that would also be 0.042b. Water, we just put a line through. And for ammonia, the change in concentration would be negative 0.042b. For the equilibrium concentrations, we would simply add up the columns, which gives us B minus 0.042b. Water, we just put a line through. Equilibrium concentration of ammonia is 0.042b, and that completes the ice table. So what's important for us here is the bottom line, which gives us the equilibrium concentrations. Now we can write the expression for our equilibrium constant, which is Kb equals the concentration of the products divided by the concentrations of the reactants, which in this case is the concentration of NH4+ times the concentration of hydroxide divided by the concentration of ammonia. Substituting in the values, we get 1.76 times 10 to the minus 5 for the value of Kb for ammonia times 0.042b for the equilibrium concentration of ammonium, and 0.042b for the equilibrium concentration of hydroxide, and b minus 0.42b for the equilibrium concentration of ammonia. Simplifying, we get 0.042 squared times b squared divided by 0.958b. Solving for b gives us 0.958 divided by 0.042 squared times 1.76 times 10 to the minus 5, which gives us a value of 0.009558 for the value of b. Now remember, b equals the initial concentration of ammonia, and so the final answer is 0.0096 moles per liter as the initial concentration of ammonia.